Design of concrete structures, chapter 4, flexural analysis and design of beams, example number 3. In this example, we want to analyze the last part of this stage of analysis, which is the ultimate load or flexural strength design. Then FCC compressive strength in concrete is higher than a half of F prime C. If you remember, in replacing the actual distribution, this parabola with the rectangular distribution of Whitney, if you develop the balance condition, this summation of forces goes zero. In that case, summation of Fx goes zero, and the compressive part of concrete is equal to tensile part of steel in terms of their forces. If you calculate A based off that, that gives us the height of concrete block of equal to AS times Fy over 85% of F prime C times B. And if you remember, we just had a table which gives us the beta A, alpha B, beta 1, and also gamma value. So to calculate the last condition, which is the nominal moment Mn calculation, so if we do know what the height of concrete block, height of equivalent block of concrete is, Mn then is a 85% of F prime C times AB, which is Cc, times the moment, which is D minus A over 2. And if you just replace A from this equation down here and rearrange the equation, it just gives us a nominal moment of equal to rho times Fy times BD squared times 1 minus 0.59 rho times Fy over F prime C. That's the nominal moment calculation. In this example, if we just want to, if we have all the same, everything is the same like the last two examples, but the difference is this time we want to determine the nominal moment Mn at which the beam will fail. So again, formula of Mn is provided. We just replace that in our values in Mn formula. And it just gives us rho. From here, it just comes from the division of, if you divide area of steel over B times D of the block, it just gives you the density of steel, which is 2.37, which is the area of steel, over D, which is bits of concrete block, times 23, which is the effective depth, and it just gives us this numeric value. And just yeah, and if you replace that, it just gives us a nominal moment of 248 feet times kilopounds. So if come back and calculate the height of concrete block, it just gives us AS times Fy over 85% of F prime C times B, and it just gives us a height of equivalent block of compressive concrete equal to 4.18. And if you remember from the Whitney blocks, it just says A is equal, the height of concrete block is just equal to beta times C or X, which is the distance from the top edge to the neutral axis. So if A is equal to beta times X, then beta is 85.85 for a F prime C equal to 4000 psi. And if you just rearrange the equation, it just gives you X is X is equal to 4.18 over 0.85, and that's 4.92 inches. So that's the distance from the top edge to neutral axis. And if the interesting part, if we want to make a comparison between three scenarios, the first one, which when we have a elastic stress and on cracked section with the moment of 45 feet times kilopounds, we have our y bar or neutral axis from the top edge equal to 13.2 inches FC and FCT, because in when our section is not cracked, we have concrete in both parts, so we have a FCC and FCT. So a concrete in compressive part and concrete in tensile part, and also we do have FS, which is the stress in tensile stress in uh, steel rebars. Likewise, in second scenario, which we do have stress, we do have elastic section yet, but the section is cracked already. So in this case, we do have a distance from top edge equal to 7.6 inches this time, and FCC compressive part of concrete is equal to 1319 psi, and FS is 22,261.67 pound square inches. You can compare with the previous part and you can see much higher in terms of numeric value. And in the last scenario, which is the nominal moment calculation, which locates in an ultimate load design condition, definitely x or neutral distance travels all the way high to x equal 4.9 inches in comparison to two previous condition, and Fs is just the yield stress of all steel, and that's 60,000 pound square inches. So as a conclusion, when the concrete had not yet cracked in tension, the neutral axis was located in a distance of at a distance of 13.2. As the section cracked, but the steel is elastic, it just moved a bit higher to 7.6 inches, the distance of top edge to neutral axis, and if it immediately before the beam fails, the distance traveled upward farther to reach 4.9 inches in in terms of the distance of neutral axis to the top edge. And also for the same stage of loading, the stress in the steel increases in the very first part. In when we have elastic section and uncracked section, the stresses in the tensile stresses in steel was 20 tensile steel stress was 2870 psi. Then when we are still in an elastic domain, but the section is already cracked, it just moves to a 22,300 psi, and all the way before failure of the section, it just reached to the yield stress of steel, which is 60,000 psi for 60,000 psi for our problem at the nominal moment capacity. Also, the migration of the neutral axis, which we talk about it from 13.2 to 7.6, then to 4.9 inches, was an interesting due to a stage behavior in the behavior of concrete in different stages. And also, this example also illustrates that the fact of that the nominal moment cannot be determined from elastic calculation, because it's already in non-elastic domain. So we need to go with ultimate load or maximum flexural design. And at the same time, other interesting result is most of bending moment capacity of beams is after cracking. So the very first scenario, nothing, no cracks. We have the entire section, and you can easily see uncracked an uncracked and elastic section. We have cracked and elastic section. We have cracked and non-elastic section. So for the first time, for the first part, we have a 13.2 inches. It just decreases to 7.6 and ultimately to reaches to 4.9 inches at the last scenario. If you make a comparison between a tensile stress in steel from the uncracked elastic section, which is 2,873 psi, it increases to 22,261.667 pound square inches. And finally, it just moved from 22,000 to yield stress of steel, which is 60,000. And at the same time, if you remember, the moment capacity for the first one was 45 feet kilopounds. The other one increases, the second scenario increases to 60 kilopounds. And you can easily see from the, as if we move from the elastic domain to non-elastic domain, there is a huge gap between moment capacity, which is 60 to 248 feet kilopounds. Thank you. We'll solve more problems.